Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. To fully grasp the significance of hubs and bridges, it's important to understand how they differ from one another in terms of their function, the OSI layer they operate on, and the logic they apply. A hub functions purely at layer 1, the physical layer, and does not interpret or make decisions based on any part of the data being transmitted. It blindly repeats all incoming signals to all other ports. A bridge, by contrast, operates at layer 2, the data link layer, and uses MAC addresses to forward frames selectively. This difference in logic allows the bridge to reduce unnecessary traffic and isolate collision domains, something a hub is entirely incapable of doing. The exam consistently includes hubs and bridges because they serve as important comparison points to modern networking devices. Even though these devices are mostly obsolete in real-world networks, their behavior illustrates key concepts like collision domains, broadcast domains, and the roles of various OSI layers. You may encounter exam questions that use legacy equipment to set up a scenario or to test your understanding of how network traffic should flow. You might be asked to distinguish between devices by their behavior or function within a topology, especially when identifying the root cause of performance issues or traffic flooding. When comparing how hubs and bridges handle network broadcasts, the difference becomes clear. A hub doesn't distinguish between broadcast and unicast traffic. It repeats everything it receives. If a frame is sent to a single MAC address or to all devices on the network, the hub treats them the same. Bridges, however, are more selective. Although they do forward broadcast frames, they use MAC address tables to make decisions about unicast frames, reducing the volume of unnecessary traffic. This selective forwarding minimizes network congestion and allows for more efficient use of bandwidth. You may see network diagrams on the exam that include outdated technologies like hubs or bridges. Their presence in these diagrams is not accidental. They are included specifically to test whether you understand the operational differences between these older devices and modern alternatives. Recognizing a hub in a diagram should immediately alert you to the possibility of a single, shared collision domain and high likelihood of collisions. Spotting a bridge, on the other hand, means you need to think about how it's segmenting the network and isolating traffic between its interfaces, based on MAC address learning. Knowing which layer of the OSI model a device operates on is a critical part of the exam. Hubs are layer 1 devices. They work with electrical signals and do not process any address information. Bridges operate at layer 2, making decisions based on MAC addresses. Switches also operate at layer 2, but they are often described as multi-port bridges with faster internal logic and better scalability. This distinction between layers is essential not only for exam questions, but also for developing a correct understanding of how network traffic is managed and forwarded across a topology. Switches eventually replaced hubs for several compelling reasons. One major benefit was the ability to create separate collision domains for each port. While a hub placed all devices into the same collision domain, a switch isolates each device into its own, allowing for full duplex communication and preventing data collisions. Switches also use MAC address tables to direct traffic only where it needs to go, rather than flooding it to all ports. This makes networks faster, more efficient, and better suited to modern applications, with high bandwidth demands and real-time communication needs. Likewise, bridges were replaced by switches due to scalability concerns and limitations in performance. Bridges were generally limited to 2 or 3 ports and could not handle large-scale network environments. Switches, on the other hand, are capable of managing dozens or even hundreds of ports simultaneously. They use advanced integrated circuits to perform MAC address learning and forwarding at high speed. Switches also support features like virtual local area networks and loop prevention protocols, which bridges were never equipped to handle effectively. Legacy devices like hubs and bridges remain valuable to study not because they are used today, but because they help explain why modern networks are designed the way they are. By understanding how hubs failed to segment traffic and how bridges made incremental improvements, you can better appreciate the leap in functionality offered by switches. This historical progression helps reinforce your comprehension of key networking principles, especially those related to traffic flow, segmentation, and the logic behind device behavior at different layers of the network stack. Knowing the simple operation of hubs and bridges provides a reliable foundation for tackling more advanced topics. A hub's lack of logic and its broadcast everything behavior illustrate what happens when networks are unmanaged and congested. A bridge's simple decision-making, based on MAC addresses, introduces the concept of filtering and learning. By starting with these foundational devices, you can better understand how modern technologies like switches, routers, and firewalls manage data more efficiently and securely across complex environments. To summarize the essential traits of hubs and bridges, think of hubs as the most basic device. Repeating everything, operating at layer 1 and offering no traffic control. Bridges represent an evolutionary step, offering MAC-based traffic forwarding and collision domain segmentation at layer 2. Though they are rarely used today, these devices shape the design principles of modern networking. For the exam, being familiar with their roles, behaviors, and limitations will help you identify the correct devices, troubleshoot historical topologies, and understand the underlying reasons for adopting more advanced technologies. Exam scenarios may use outdated topologies, specifically to test your ability to recognize problems caused by legacy equipment. You might see a question describing excessive collisions, unexplained traffic flooding, or slow performance, all within a network using hubs. The correct response could involve identifying the hub as the cause and suggesting its replacement with a switch. Similarly, bridges may be mentioned to prompt consideration of how MAC address filtering works, or to evaluate your understanding of collision domain separation. These are opportunities to apply your foundational knowledge in a practical, exam-focused context. As you prepare for the exam, keep in mind that legacy devices are not just relics of the past. They are stepping stones that reveal how networking evolved. They clarify why switches and routers perform the way they do, and why certain architectural decisions are now standard. The more you understand about the origins of network segmentation and traffic management, the better equipped you'll be to answer questions about current technologies. This depth of knowledge not only improves your test performance, but also prepares you for more advanced topics in networking and infrastructure. By knowing how hubs and bridges worked and failed, you'll be better prepared to answer questions about how traffic should be handled, how devices communicate, and how networks were historically managed. Every limitation of these devices has a corresponding solution in modern equipment, and those contrasts are central to the exam's way of testing your comprehension. That's why learning about legacy devices is not wasted effort. It gives you the baseline understanding needed to analyze how far network design has come and where it's headed. Understanding the contrast between hubs and bridges reinforces your ability to interpret network behavior and to diagnose problems effectively on the exam. Hubs create a single collision domain across all connected devices. This design choice, while cost-prohibitive at the time, led to significant performance degradation as more devices were added. By contrast, bridges isolate traffic between interfaces, allowing each segment to function more efficiently. This segmentation capability is essential knowledge, as it forms the conceptual basis of modern switch operation and how network administrators control congestion and reduce unnecessary traffic. Another way to think about hubs versus bridges is to consider their effect on network size. Hubs do not scale well. Adding more devices increases the chance of collisions without improving efficiency. Every additional node becomes a liability to performance. Bridges, while still limited, allow a modest form of network scaling by keeping traffic between segments separate. Though limited in port count, bridges enable more thoughtful layout of small networks. This behavior set the precedent for today's high-speed switches, which integrate these principles on a much larger scale and with much higher throughput. Even though bridges improved upon hub limitations, they still lacked many features expected in today's devices. For example, bridges did not support dynamic network segmentation like VLANs. They were also incapable of managing complex topologies or preventing broadcast storms without manual intervention. Today's switches include these features natively, allowing for not only scalability, but also enhance control and resilience. Still, understanding the simple Mac-based filtering of bridges provides essential context when you begin studying switch learning and traffic optimization mechanisms on the exam. In addition to technical behavior, the exam may also test your ability to identify devices based solely on descriptions or diagram placement. You might be shown a diagram and asked to label a device as a hub, bridge, or switch based on its traffic pattern. For example, if a device repeats all data to all ports without filtering, it must be a hub. If the device forwards data based on MAC addresses and connects two segments, it is a bridge. And if it provides isolated paths between many devices while supporting modern features, then it's likely a switch. These distinctions are small but critical to accurate interpretation under test conditions. An important distinction to keep in mind is that while hubs and bridges were used in legacy networks, they did not disappear all at once. Their phase-out occurred gradually, and for that reason you may still find them in older topologies, diagrams, and exam questions. Understanding their presence is more than historical curiosity. It is part of how the exam verifies that you know which devices belong where, how they behave, and what their limitations are. Knowing that a hub cannot prevent collisions or that a bridge cannot scale beyond a few segments allows you to choose appropriate solutions when network issues are presented in exam scenarios. The replacement of hubs with switches brought measurable benefits that the exam expects you to understand in detail. Switches eliminated the shared collision domain by giving each connected device a dedicated segment. This allowed simultaneous full duplex communication, drastically improving efficiency. Switches also introduced rapid MAC address learning, reducing broadcast traffic and enabling precise delivery of frames. These improvements are not just operational, they are testable concepts you need to recognize, especially when asked to identify why a network is or is not performing optimally. In the case of bridges, their replacement with modern switches was driven by the need for greater flexibility and port density. While a bridge typically supported only two interfaces and required manual configuration in more complex environments, a switch could handle dozens of ports automatically. Switches support modern protocols like spanning tree and trunking, which make them capable of managing loops and handling traffic from multiple virtual networks. These features are entirely absent in bridges, and this absence is a common source of confusion that may be tested. Make sure you understand not just what a bridge does, but also what it cannot do. Legacy device awareness also helps in understanding specific packet behaviors. When a packet enters a hub, it will be duplicated and sent to all other devices, increasing the chances of collision and offering no privacy or security between nodes. With a bridge, the packet is examined for its MAC address and only forwarded if needed. This filtering makes a bridge a smarter solution, but only to a point. It does not offer the high-speed internal switching, error checking, or advanced quality of service found in modern switches. This contrast will help you evaluate different device choices on the exam more effectively. It's also essential to recognize that both hubs and bridges still follow certain behavior rules that influence their exam relevance. Hubs always flood traffic. Bridges flood only when they do not know the destination MAC. If the MAC address is known, the bridge forwards the frame to the appropriate port. Otherwise, it acts much like a hub, broadcasting the frame to all other ports. This nuanced difference is small but important and often tested. Recognizing when a bridge will flood and when it will filter depends on understanding how it builds and references its MAC address table. The OSI layer model often forms the backbone of many exam questions. Knowing that a hub resides at layer 1 and a bridge operates at layer 2 allows you to identify where in the network a failure or inefficiency might be occurring. For example, if a problem is related to collisions and no addressing is being performed, it likely involves a layer 1 device like a hub. If the problem involves incomplete MAC tables or segment filtering, the issue might lie at layer 2 with a bridge or switch. Mastering these distinctions allows you to pinpoint issues quickly and confidently during the exam. Just as importantly, recognizing these legacy devices helps you avoid incorrect assumptions. For example, if a hub is part of a topology, full duplex communication is not possible, and all devices must share bandwidth. If a bridge is present, traffic might be better managed, but scalability remains limited. These constraints should guide your interpretations of network diagrams, performance problems, or optimization questions. The exam may ask you to explain why a certain device choice would or would not be suitable for a growing organization. In such cases, referencing the limits of hubs and bridges directly helps justify your reasoning. Finally, by learning about legacy devices, you're not just studying outdated technology, you're building a mental framework that allows you to understand the why behind today's network design choices. Switches did not appear without reason. They were developed to solve very specific problems that hubs and bridges could not handle. Every limitation found in those older devices has a corresponding solution in the newer ones. Whether it's segmenting traffic, isolating collisions, or learning MAC addresses efficiently, these improvements have shaped how networks are built today. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.